All right. So on this one here, guys, both of these questions were chosen because they illustrate the need to read the question carefully. And I forgot to erase the underlined part there, okay, that basically tells you question number one is not a law of conservation of energy question, is it? No. Okay. It has, first off, the word work in it. And work is a what of energy? A change. In a conservation of energy question, energy doesn't change, right? It stays the same. So, okay, we got to be looking at things like that, little keywords that can help us decide what kind of question it is we're dealing with, okay? Also, in this one, we've got an object that's being lifted, and pretty much every conservation of energy question we've had has involved something going downwards, right, from a higher point. So, not that they have to be that way, but that's typically the way they go. All right, so for our first question here, give them a mark for their givens. Okay, they were told that the initial height of the construction materials was 10 meters. The final height of the construction materials was 35 meters. The mass of the construction materials was 200 kilograms. Now, we're looking for how much work is done, so give them a mark for correctly identifying this as a work energy theorem question. Work is a change in energy, or maybe they had EPF minus EPI, something like that. Our next mark will be for putting in the formulas. So MGHF, our final potential energy, minus MGHI, our initial potential energy, because is the kinetic energy changing in this question? No, at least there's no mention of it. They don't tell us any speeds, so we can only assume it's not. And then we've got to put in our work. So give them a mark if they plugged in their numbers. That's 200 kilograms times 9.81 times 35 minus 200 times 9.81 times 10. Okay, and that should come out to 49,050 joules. Hold on. So a lot of people like shortcutted this question, which is fine, okay? And they just took the change in height. They went 35 minus 10 and then went 200 times 9.81 times that, and that's fine, okay? I just always show you the long way because my fear is that you'll start doing that with speeds when you're dealing with kinetic energy. Will that work? It will not. They're squared, okay? It just doesn't work the same way. So please make sure that if you're doing that, you're only doing it here. Yeah, if you got the right answer, you can have all the marks. Yeah. I just always say you should show every bit of work because I can give you marks for it. Yeah. Yes, guys, if they put this in scientific notation, I know that was something that I talked about in the podcast yesterday, and I'll review it just a little bit today or talk about it today. Okay, this in scientific notation is 1, 2, 3, 4, 4.9050 times 10 to the 4 joules. Okay, it's not like scientific notation is that difficult a thing, but okay, that's what that number looks like in scientific notation. Okay. All right. Victoria. Yes, that's fine. Yeah. All right. Any other questions on number one? Okay. So question number two is a law of conservation of energy question. It's a bobsledder going down the bobsled track. Okay. What we know is that their initial height is 45 and their initial speed is 12 meters per second. Their final height is 13 and their final speed is unknown. So we can call that givens. If they drew a picture or wrote their givens out, give them a mark for that. Okay. Also, give them a mark for recognizing that this was a law of conservation of energy question. EI equals EF, or maybe they expanded it out to initial potential plus initial kinetic equals final potential plus final kinetic. Okay. Then we want to start our manipulation. Okay. We need to get VF by itself. Okay, and so we need to get EKF by itself, so we would subtract EPF over to the other side. It doesn't matter whether they did this in this order or not, as long as they show this generally. Okay, that would mean then that I have MGHI plus 1/2 MVI squared minus MGHF equals 1/2 MVF squared. So they have some of this stuff here. You can give them 2 marks for getting kind of to that point, including possibly crossing off the M's, because I don't think I gave them to you. Okay. Mason. I would show a little more than that. I would show a little more than that. just in case. I mean, if you get fat fingered on the calculator and you mess it up, I want to be able to give you as many marks as possible from you demonstrating you knew all the steps. Yeah. All right, so we go straight to here, okay, to manipulating for VF. So now we're going to divide both sides by 1/2 and square root. So that's this. If they have that, they can have another mark. Okay, plugging in our numbers, we got 9.81, okay, times 45 plus 1/2 times 12 squared. So kind of our initial, okay, minus our final potential, 9.81 times 13 divided by 1/2, okay, and that comes out to 27.8 meters per second for their final answer. And that one is out of 6 marks, as would a question like that on the unit exam or final exam. She didn't show the square root, but she did it. Unfortunately, no. She either got really lucky or, yeah.
So is that 2 off?
Actually, you know what? She got the right answer. Give her the full marks. Okay. So give them guys a mark out of 11, right? Yeah, give them a mark out of 11. Okay, let them see it. Then pass it to the front of the row, please. So on this particular question, okay, if anybody jumps out of a plane in the perfect physical world, they will continue to move along at the same speed as the plane while falling. Okay? The only thing that slows you down in the real world is that the plane is under power and can maintain a constant speed, and you hit this wall of air that slows you down really quickly. Okay? But in the real world, or sorry, in the perfect physical world, not the real world, okay, you would continue to move at the same speed as the plane horizontally. Right? Because there'd be nothing to slow you down and nothing keeping the plane from going faster or slower. So, okay, it's the same thing that would happen if you were in space and you just put something out beside the ship. Okay, it would just keep moving along beside you because you and the ship are moving at, or it and the ship were moving at the same speed, unless you start accelerating the ship, and then it would fall behind. Right? Yeah. Yep. Yeah. As long as the ship's not accelerating, they're okay. Yeah. Okay. We'll have a look at that next week.